Now I'm going to put Taylor series to work. For this class, that means I'm going to integrate using Taylor series. Let me start off with a function that up until now would have given me trouble. This is the function sine of x divided by x. And I would like to calculate the indefinite integral of this function. Now, of all the techniques that I know, doesn't look like U substitution is going to help me here. Maybe I could try integration by parts. But I'll tell you right now that that will not be very fruitful. This integral right here is special. There's lots of functions like this where the integral is called non-elementary. I don't want to talk very much about the theory because that's a bit outside the purview of this course. But the short of it is that this integral, this function, this antiderivative, actually cannot be written as a finite combination of elementary functions, the power functions, the sine and cosine, and so on. But the operative word there is finite. And I actually have the tools necessary to work with this problem, just I'll need to use power series. So what I'm going to do in this situation, if I want to integrate using power series, I will need to rewrite my integrand. The very first thing I'm going to do is I'm going to separate off that 1 over x, and I'm going to use a power series representation of the sine function. I have one in mind. I'm going to use the Maclaurin series, or you might prefer the Taylor series of the sine function centered at 0. Either vocabulary you like to use, the coefficients will be the same. The sine function is equal to the summation, n goes from 0 to infinity, of -1 to the power n divided by the number 2n plus 1 factorial. And then I'm multiplying by x to the power 2n plus 1. And this is still an integral, so there'll be a nice dx capping off the end to remind me what the variable I'm using is. Now, I would like my integrand to just be a power series. Right now, it's a power series times this fraction 1 over x. But that's workable. What I'm going to do is I'll say that if I'm dividing by x, and I have a sum of a bunch of different powers of x, then all I have to do is knock off 1 power of x from each that I see. Now, in my sigma notation, the coefficients are going to be the same. -1 to the power n divided by 2n plus 1 factorial. But because I divided through by x, I'll just have x to the power 2n. Now what I'm going to do is I'm going to switch the order of my integral and my summation. Right now, the integral sign is on the outside. The sigma operator is on the inside. I'm going to switch it so that instead of an integral of a whole bunch of powers of x added up together, I'm going to add up a whole bunch of integrals of x's to various powers. And that might seem like shuffling the deck chairs on the Titanic, but it actually does a job here. Because I can integrate this power series 1 power at a time, the same way I do for polynomials. If I have x cubed plus x squared. I separate them first. I do the antiderivative of my x cubed. I do the antiderivative of my x squared. At the end of the problem, I put them back together. This is the same idea. It just looks a little bit different for the fact that I'm using sigma notation with the infinite product. Now, it is important that this switch from line 2 to line 3, this works only because the power series I'm looking at is convergent. If I try this for a series that's divergent, then I can get some really nonsensical results. But I've picked these examples here that won't happen for these problems. Now, at this stage, I am still adding a bunch of terms up, but now I have the ability to use the power rule for integrals. Where before I had x to the power 2n, if I'm integrating, I will increase that power by 1. I divide by the new exponent. This is now x to the power 2n plus 1, all divided by 2n plus 1. The coefficient in front is going to stay the same as what I had in the previous line. So there is the calculation of my antiderivative. The very last piece that I'm going to put here, because this is an indefinite integral, there will be a constant of integration. So I'll have a plus c outside of the power series. One thing to note here, because I'm doing an antiderivative, and because I have the plus c, the constant of integration, the power series here actually will not have its own constant term in a way that gets sucked up into the plus c. So if you were expecting to see a constant in this sigma notation, it's just not going to be there. For n equals 0, that's the smallest exponent I could get. And I'm guaranteed to have whatever my exponent was before plus 1. For power series, we'll just never get a constant back. Okay, let's look at another example. So instead of integrating sine of x over x, let us take a peek at the exponential function. So I want to integrate e to the power minus x squared. Doing that is going to require that I have a power series for the function e to the minus x squared. So off to the side, I'm going to try to calculate what that would look like. I happen to have this series memorized. It's a handy one, but if you need to reference your textbook, that's fine as well. The Maclaurin series for the ordinary exponential function is that e to the power x is equal to the sum from n equals 0 to infinity of x to the power n divided by n factorial. You can look that one up. That's not quite the function I'm interested in. I want e raised to the power minus x squared. Now, because the Maclaurin series is guaranteed to converge for all values of x, that's a special property of the exponential function. It has an infinite radius of convergence. Well, I can just substitute. And I'll do whatever I need to keep the equation balanced. So everywhere that I used to see an x, say if I'm raising x to the power n, I will replace it with minus x squared. And I would encourage you to be careful about the parentheses as you do this. So there is my power series. This is the sum, n equals 0 to infinity. And since I'm raising this to the power n, I'm going to write my terms as -1 to the power n times x to the power 2n, all divided by n factorial. And this power series is the integrand for my indefinite integral. Now comes time for the main trick in today's lecture. I'm going to push the integration sign inside the summation. And I'm going to use the power rule for derivatives. Everywhere I see a power of x, all I need to do is increase that power by 1. So I now have x to the power 2n plus 1, all divided by 2n plus 1. The coefficient that I had out front before stays the same. -1 to the power n divided by n factorial. So this will be my summand in the power series. And again, I'll have a constant of integration outside of the summation, because this integral won't actually be able to produce constants on its own, even though power series are supposed to have a constant in them. Let's look at another one of these where I'm going to manipulate a Maclaurin series I already know in order to match the function that I'm interested in. Here, I want to integrate 1 divided by 1 plus x squared. This is a rational function. And for integrating a rational function, we've previously talked about the partial fraction decomposition of rational functions. That will technically work here, but it will be a bit of a mess. I'll need to factor a degree 6 polynomial. And while there is a factorization here, this denominator does not have any real roots. So I will be needing to use something clever to find my factorization. On the other hand, I won't need factorization and I won't need partial fractions if I use Maclaurin series instead. So I'm going to see what I can do using the geometric series formula. The function 1 over 1 minus x, well, that's a rational function, but it's also the result of the geometric series. And I know the geometric series starts at n equals 0, goes up to infinity, and my summands are just x to the power n. This power series only converges as long as x is a number between -1 and 1. So I do need to be careful about that. But under that assumption, I would be able to use this expansion. I just need to find a way to manipulate the formula and make it look like what I have on the left of this screen. So I need to have subtraction in my denominator, and I'll say that my denominator is the number 1 minus the quantity minus x to the 6th. That gets me the formula that I want. It's written in a bit of a funny way, but whatever gets the job done is allowed. I haven't broken any rules of algebra writing this. It just looks a little clumsy for a moment, and that's okay. Once again, to keep this equation balanced, I'm going to replace the x that I see on the right-hand side by minus x to the power 6. And I'm going to be careful with these parentheses as well. As a side note here, I do need to make sure that I'm still within the right interval for this power series to converge. X has to be a number between -1 and 1. And by taking that number to the 6th power, all I've done is I've made it smaller. So that's fine. I also flipped the sign to negative, but again, that's not going to change the magnitude of the number. So I'll write this out using the series expansion. I have the integral of the sum, n from 0 to infinity. And once again, I'm going to break this up and say that the coefficient is -1 to the power n, and the power is x to the power 6n, integrating with respect to x. Switch the sigma and the integral sign so I can calculate using the power rule. My antiderivative of -1 to the power n times x to the power 6n will be -1 to the power n times x to the power 6n plus 1, all divided by 6n plus 1. Sigma is still present because I am expecting a power series, but this formula is still enough to specify a function of x. So this formula here, with the constant of integration, solves the integral. That is my antiderivative. Just, it happens to be written as a power function, a power series, rather than some closed form thing. That is the price that I pay, but, you know, I kind of prefer integrating, where the only rule I need to know is the power rule. Somehow it feels far, far easier than all the techniques that we learned in the first couple weeks of class. Those are still important, of course, but it's nice to see that with a little bit of theory, I can make my life so much easier. Now, for the last of these, I'm going to integrate e to the power x divided by x. And the method that I use is still the same. This will resemble that sine function from the very beginning of this video. There is one small deception here. One thing we have to be careful about. Now, I remember that my power series representation for the exponential function is x to the power n over n factorial, add up from n equals 0 to infinity. Now I'm going to divide everything I see by x, which means that I'll have the sum from n equals 0 to infinity of x to the power n minus 1, all divided by n factorial. Integrate with respect to dx, and bring the integral sign inside, see what I get. Now, the problem here is that there is one, and only one, exception to the power rule formula. If I try to integrate x to the power -1, I do not add 1 and divide by the new exponent, because then I would get x to the power 0 divided by 0, and that just doesn't work. The exceptional case says that the antiderivative of x to the power -1 is the natural logarithm function. And you might not immediately see it, but with n equals 0 as the starting point for this series, I do end up with an x to the -1 power. Power series are only supposed to have positive exponents, or 0, we let them have constants, but we do not let power series have negative exponents. What happened? Well, when I divided through by my x up at the first line, it stopped being a power series. So I can still do this, I just need to be very careful. When n equals 0, I will be integrating x to the power minus 1 divided by 0 factorial. That's fine. 0 factorial is 1, and I can calculate this antiderivative. I just need to do it separate from the rest of the series. So starting from n equals 1 to infinity, x to the power n minus 1 is guaranteed not to be an exponent of -1. The smallest exponent I can see here will be 0. So from this -1 term, I will have the natural logarithm of the absolute value of x. And to that, I will have to add on the series n from 1 to infinity, x to the power n divided by n factorial, and then divided by n. And finally, there will be a constant of integration on here. So this expression now has a logarithm in it. That was a bit of a surprise. But as long as I'm careful when I do this division and I recognize that, oh, I do need to use the natural logarithm for my antiderivative, this is still within my power to calculate an antiderivative. And that's it.